the slides, the photo of the notes actually. Last week we finished almost completely the part of the nuclear reaction. I left you with the S and R process. S and R because there is a competition among two reactions. One is neutron capture. Yeah, but if I share, it's better. This morning I'm okay. Now it's okay. You have neutron capture when a nucleus capture a neutron and goes to a higher mass number. Then there is the other process that is the beta minus or beta decay, where an unstable isotope of an element, a neutron, decay, and in a proton and an electron, the electron goes away with an antineutrinos, and it's we have an element of higher atomic number. As I said at the beginning, remember conservation of everything, mass, baryonic number, in lepton number. So above just enter a neutron, so it's raise up the mass number. Below, since we have beta decay, the neutron goes to a proton. So here increases the theta. A is the total number of neutrons stay the same. So actually is the sum of the baryonic number on the reaction. So is the same. But since we emit an electron, that is a lepton, before we have no lepton, we need an anti-lepton to keep the lepton number 0. So you emit an electron also to keep the charge the same, Z at the beginning, Z should be at the end, and then put the antiparticle to fix the sum of the total leptonic number. As I said, using the conservation, it's easier to try to remember perfectly each reaction. You remember the mean, and then you add particle to fix the conservation. Because to remember if it's neutrino, antineutrino, it's tricky. But if you use the lay to remember it, straightforward. Then if you have a lot of neutrons, so you have that the velocity of the neutron capture is definitely higher than the velocity of the beta decay, you have what is called a rapid process, in the sense that you rapidly fill the atoms with new nucleons. Instead, if you have the neutron capture is not so fast, so the beta decay happen quicker, you have what is called the slow process. This means that the raise of the mass number is slower than how fast the neutron manage to decay. Neutrons are a tricky particle, doesn't like to stay alone. Usually neutron, so alone, not inside the nucleus, decay within 1,000 seconds. It's but quick to decay. Only case when you can have almost free neutrons stable are in neutron stars, but this is because we'll see they cannot decay because as we saw, to have the beta decay you need to emit an electron. Usually when a neutron star is formed, the electrons are so packed that are in a degenerate state and also relativistic. So you cannot emit the electron because it's not permitted. Inside the nuclei, if you have too much neutrons, equally can start to be radioactive. The isotope is not stable and decay in proton and electron. The beta decay, the velocity of mean life are almost constant with respect to the physical properties of the gas, temperature, density. It just depends on the nucleus, on the stability of the nucleus. Some nucleus are really stable, there is not, some are unstable and will decay. Why? And neutron capture vary with temperature and density. This means that the combination depend favor one channel or the other, so you have the two process, the law and process, depending on the environment. We'll see that some process happen more in a certain moment than the other. Essentially, for their process, you need a really high production of neutrons really quickly. So the atom, also if an atom is not stable, have not time to decay and can enter another neutron. Another point for there are some always in the nuclear reaction are not from new element, but is important. It's the pair production when a photon, gamma ray, obviously, react with an ion and produce a pair of particles. In this case, talking about a pair of electron positron. That then the positron can react with an electron, annihilation, and the production of two gamma. You need an ion to have a perfect conservation of energy and momentum. So it's also when they annihilate with each other, they produce not one gamma, but two. Because otherwise you cannot conserve both energy and momentum. You can see the electron and positron have a mass about half mega electron volt, so you need a really high energetic photon gamma to manage to produce this kind of reaction. As we saw previously, the effect of ionization, the effect is similar because the photon produce interacting with ions produce a pair that then annihilate, but at certain point there is an equilibrium between the production of the pair and the destruction. So we have a certain population of positron inside. So we subtract energy from the radiation pressure to put in the gas. And the effect is similar to ionization. If you increase the temperature, the number of the particle increase. If you increase the density, the number of particles will decrease because it's easier than the positron can annihilate with an electron. As so, since it's similar to ionization, the effect is also similar the effect with the adiabatic coefficient that can vary its value according to the presence of this pair. Another point, don't be scared by the formula, but is neutrino production. That is important because, as I said, neutrinos are mainly lost energy. You only in the latest phases of a massive start you can have some interaction of the neutrinos with matter. Otherwise, just they are produced and they see almost the star as transparent and pass through it quickly. We can have photoneutrinos as a similar. A photon interact with an ion and produce a pair. One of the channels, as we talked about in reaction, for each reaction among particles, you can have several channels that are going outside. One of these channels that's probable is also production a pair of neutrinos, electronic neutrinos, and you can see here the energy loss, essentially. What on the point interesting is to check on the independence. You can see that almost all of this reaction have a strong dependence on the temperature. That means with the temperature that was higher, the energy loss is really important, but also that the temperature goes down, the energy loss is almost negligible. You remember that if you linear quadratic, when you goes up with the okay, this maybe what you for if you go should be here. In the power, they pass always from 1 and 1, but for less than 1, that goes always nearer the value of 0. So it's this other this factor that below certain temperature, almost the production is negligible of this effect. In this case, at 100 million of Kelvin, the epsilon is more or less 1, minus 1 is the order of 1, and we see later why this is important. Per neutrinos, it's similar, but you have the like in the photo production pair is the annihilation of two electron and positron. Instead of producing two photons, can produce a pair of neutrino and antineutrinos. This is the formula. You see really quite strong dependence, and again a fraction of billions of Kelvin, the value is almost 1, then started to increase. Plasma neutrino, it's a peculiar phenomenon. Saying quickly, the photon, when they're moving inside the plasma, can do all the calculation and they can behave like they are the boson, but with a rest mass. They are boson, they have no mass, but when they're moving inside the plasma, since the propagation is a bit slower than the top speed of the light in the vacuum, they present this effect, so they manage to produce neutrinos, and this is the formula. It's quite complicated. And but you see, here is not simple calculated because it depends on several things. But anyway, if you go too low, it's negligible, and at higher start to increase a lot. No, here it's not so strong. Then we have the Bremsstrahlung, as we saw previously in the opacity. In this case, the photon, the electron that interact with the nuclei can emit a pair of neutrino and antineutrino instead of a photon. With this formula and this range 100 and 200 million of Kelvin, epsilon, it's almost on the magnitude of 1. Also here it's a minus, obviously. It's because neutrino is energy you're losing. Per Bremsstrahlung, you in general you'll I think also in general for neutrino production you have a range of density between 10 to the 2, 10 to the 9, temperature around the millions. Why this? At the beginning, of the nuclear reaction, we calculated the epsilon, mean epsilon, that was just 2 and erg by gram and per second. And we show that the true one in the core can be calculated accordingly using let's go there, make it easier. Easy. This is easier. This is the mean, the real, depend on luminosity, but not on all the mass. It depends on the fraction of the mass that is the core, because the nuclear reactions are actually just in the core. So we have a mean value of 2 and a real that we cannot determine outside, but we can determine doing some calculation. But this means also that we have this real, since we know how much is the luminosity, we can calculate approximately the mass of the core. The Q value for the taken for the production of the burning, the hydrogen burning, is this one. The Q value divided the demand of nucleon is 6.5 megaelectron volt per nucleus. The total production is the Q divided I you want per mass, so the mass that we use, you have just to divide by the mass of the atomic mass, unit atomic mass, and that is essentially the mass of hydrogen. Well, not exactly, but and so we have the production by grams. Now we need a time, and we can take the time, the mean time of PP1. As we saw, it's a really long reaction that needs a lot of time to be realized, to go through. So we can take it as a typical the time for each reaction. Do all the calculation, we get 20 erg by g by per grams and per second. To calculate exactly how much is the core, we need actually consider that the core is not completely formed by hydrogen, but it's just more or less 70%, because this is the part that then can produce the energy. Another important thing, epsilon is 20. This is not depending on the mass of the stars. It's just the production of energy for the hydrogen burning, this value. So you can see that the neutrino production will be important to reduce the energy in stars. You need the temperature to be higher than a billion of Kelvin. Otherwise, it's so if the energy lost by neutrino is the order of 1, it's just 5%. It's not enough to cause some problem. But if it's sensible. But when you have a higher temperature, you start to lose a lot of energy, and this can cause a problem to the stars. Then, to do all the calculation, we can have in this way an estimation. The core is like 14% of the mass, in this case of the sun, and if you consider constant density inside the stars, the radium of the core should be like half of the solar mass. If you consider this kind of behavior for the density, it's 40% of the radius of the sun. We saw that actually it's a little less because a little, yeah, between the 30-40%, since we saw that the peak of the helium-3 fraction mass is around 0.3. So it's a good scheme. This is just looking at the sun, knowing its mass, luminosity, and calculating this value that is the production with the proton-proton. That is what is how is the sun. Just this is fun fact: the energy rate production for the human is 10 to the 4th erg by grams and second, definitely higher. It's like 500 times the one of the sun, but we have definitely less mass, so we are not shining. As you saw, the production, this means also the production is really low. But since the stars are really high mass, the mass is huge, can produce a lot of energy. As we saw, the typical time is really small, so you cannot produce a lot of energy. Like, and a last looking at the last part for the production of energy, that is the gravitational. The star can produce essentially energy in two ways. One with the nuclear reaction, and the other is the contraction. Is this just a quick showing you gravitational, by definition, gravitational potential energy, the work to bring mass from infinite to the radius we are considering. So we can calculate in general for star is gravitational potential energy that can be expressed like classical potential energy in general with the mass to square the radius multiplied by a factor that is determined by this integral. Typically, this factor is greater than 3/5.6. So the potential energy is always greater than this than 0.6 multiplied by this one. For the polytrope that we'll see soon, you can calculate that it is just exactly this value depending on the index. You have this one. But, okay, have fun. Doing calculation a little deeper with the Viriat theorem, put together, you get a little more complex, consider it not simple. You have the here moment of inertia, considering the star that we are not in equilibrium. The kinetic energy global, that means turbulence, rotation, pulsation, this kind, not the movement of the particle in the gas, but the mass macroscopic. With this value, the value on the pressure on the surface, and virial that depend on the force here. The acceleration that part of the mass can have depend on the pressure force and other force. Generally, we consider just for this force gravity. So this virial is just gravitational potential. Supposing that pressure divided density have this dependence with the internal energy by mass in this way, and then surface pressure equal to 0. You have this one that is quite usual, similar to the old one, always considering the kinetical global energy is really smaller than internal energy. Connecting with this one, considering that we have, you can have the usual consideration about the total energy, that is the sum of the kinetical energy, internal energy, potential. You can see that what is the time scale for the contraction. That is the Kelvin-Helmholtz time scale. That is essentially variation of energy that you have divided by the luminosity. What the time for which the star with a certain luminosity can shine with that luminosity, consider it just a variation of energy that is for contraction in this case. You have no internal production of energy It's just the only energy here. It's in general the macroscopic movement, but we consider that not so strong. Internal energy, that is heat, and the potential energy. As we saw, usually for a perfect gas, if a star gas collapse, half this energy go in internal energy, half goes in the change of the total energy. In this case, in the luminosity, because it's losing. Putting inside, you have this value. We are 20 million of years, depending on mass, luminosity, and radius. This is, we'll see later, but this time is quite important also for some phase of the stars. And essentially, the time is said that if the sphere of gas contract the time that we need to maintain certain luminosity just with the contraction. In general, as we already saw, for gamma greater than 1/3, you have this classical, considering no internal production energy, no nuclear reaction. The reaction in internal energy depend is a fraction of the energy released by the contraction. The other part goes in luminosity. And let's say the star emit energy. Actually, if the gamma is 5/3, that is typical for perfect gas. You have the usual alpha. If the gamma is 4/3, the energy is 0 by default. It cannot change. So you have the, if contract, all the energy goes to internal energy. There is no emitting light. But if the star has presidency energy minus the 0, because energy less than 0 is gravitationally bound. So you need that the star have energy minus the 0 to be star. Otherwise, it cannot be bound. We'll see, maybe not today, another that can happen when the star suddenly have too much energy and goes with the energy greater than 0. So if the gamma change, essentially you cannot have a star that starting with the gamma 4/3. So you are changing from above 4/3 to 4/3. Should not be perfect in static equilibrium. So we have a star up to be collapse. And if you do the calculation, essentially from the generic theorem with this one, you can see that the moment of inertia should be really small negative. That means that the star is contracted, is in collapse. For gamma minus the 4/3, the star essentially it's a situation where the gas is in continuous expansion, because it's should be that if contract, collapse, the total energy increase. So it starts to be unbound and unbound, collapsing. That doesn't make sense. So it's just the gas that cannot collapse, contract, and stay scattered away all the time. And just for completeness, doing all the calculation as before, first principle of thermodynamics, you can have a nice, at the end you can have the energy production by nuclear minus the energy lost by neutrinos, less variation of luminosity. It's, we consider it should be 0, actually can be considering also the contraction certain value, these ugly things here, that is the energy, the rate of energy production by gravity, with the contraction. It also means that if the star expand, absorb energy in this in opposite way. If you consider simple gas, you have this value. Okay, this depends on the adiabatic coefficient, but it's just for completeness. It's not like formula this strange. It's not necessarily, as I say. As a last things, time scale. Just considering this unit, the m, l, r star are unit of solar mass and solar luminosity and solar radius. Free fall, that is the time when the star manages to collapse. So you can since the equation, our equation for acceleration, it's the variation in space 1/2 the acceleration is square. You can graph, so the other one magnitude of the time of free fall is the radius divided by the acceleration of gravity. For expansion, it's the opposite. When you have not more free fall, when you have no hydrostatic equilibrium and the gravity, it's more important. So essentially, you turns down the pressure. Can happen that in some cases the pressure can disappear. Something that we mentioned a little before, like neutrino production. You can have a lot of neutrino production. That means you're absorbing a lot of radiation. That means the pressure of the radiation drops, or you are arriving to a certain moment that you doesn't produce a lot of energy with the nuclear reaction. So the luminosity is turned down, so the pressure turns down. So you have suddenly that the pressure doesn't disappear, you have the free fall. If on the other case the pressure starts to be increased too much, you have the expansion. That is the radius divided this value, that is the isothermal sound speed, because pressure it's propagate like with the pressure wave, so sound, and we can use this value to know how the pressure managed to propagate its influence inside the star. Hydrostatic time is when the two are more or less similar, so they compensate the time how variation can be stay inside, be fixed. You see, for the sun is more or less 1 hour. Then we have another two interesting for the evolution of the star, the contraction, as we mentioned, Helmholtz. That is the energy released by the contraction divided by velocity. This is at the beginning was calculated because they thought that the sun produces energy just by the contraction. And okay, this was not enough. The nuclear time scale is the same of the sky with that reaction we can produce the luminosity. So nuclear luminosity, the energy produced by the nuclear reaction divided by the total luminosity. Yeah, the total possible energy, that means the rate by second by mass multiplied by all the mass of the stars by the fraction of the element. Usually in this case we consider usually for the hydrogen burning, so fraction mass fraction of the hydrogen, and F is the fraction for the core, because obviously the star doesn't consume all the hydrogen inside, but just the one in the core. In the calculation, you get the value more or less of 17 billion years. Should be the less. But, and maybe here I didn't put the calculator for the fraction. You can put inside and luminosity, consider luminosity of the stars, it's mean the inverse of the mass to the minus 3.5. You can see that this time it goes inverse proportional to the mass, more or less the square of the mass. That means that the smallest stars have a longer life and bigger stars have a shorter life. These two is quite important because essentially the first one is the time that the star can have a certain luminosity just contracting. We'll see this is the case when we are forming stars. When the stars in the last phases is contracting and moving to contract to start the nuclear reaction. So we don't have a nuclear reaction in that contraction. The luminosity of stars is quite constant, and more or less the same of the luminosity that we will have on the mix sequence and start to produce, start to burn helium, hydrogen, that is the main production. So the Kelvin-Helmholtz is also more or less of the time that stay in the formation of the star, and below it's the stars and the time of the star in the main sequence. And we can see also here, obviously the stars, the massive stars have always a short time on the both, while the smallest are the longest time to contract and to finish the hydrogen in the center. Okay. Okay. Now we have so essentially all that we need to describe the star. We have shown the equation for this equilibrium, how the nuclear reaction are used, the pressure inside depend the gas for the radiation. In the case that is perfect gas, ideal gas, or degenerate gas, we have a single part on to describe a single part. Now we'll see that can be maybe a little bored at the beginning. It's quite boring because a lot of calculation, but quickly can give you some nice result anyway. That is studying, modeling stellar structure of the star. we put together the equation and started to use it to see how a star can behave and try to describe mathematically a star to see how, according to its mass, to the composition, we can what is his radius, what is the behavior of the pressure, temperature, density inside, and so on. The four main equation is the electrostatic equilibrium in the two form, Lagrangian and Eulerian. No, Eulerian and Lagrangian. Continuity. Electrostatic came from the motion, so no motion. The term for the acceleration is 0. If a suggestion to how to remember this formula, you know that depends here on the gradient of the pressure. On the other side, minus the gravitational acceleration, g by mass divided by r, and this is the density. And just to remember, pressure is force divided by surface. If you multiply above and below by a length, you have force by length, that is work, that is energy, and below is the surface multiplied by length, that is a volume. So the pressure is the unit of a density of energy. If you do the gradient, it's like the density of a force. And here you have an acceleration. If you multiply by mass, you have a force. If you divide it by a volume, you have a density. So given this one and this one, you have to multiply by the density to have the same unit of measurement. This is, I think, a quick way, a safe way to remember. And don't forget the minus, because the pressure goes is highest in the center and considered 0 on the surface. Continuity, but this is essentially a definition. Then is the radiating transfer in the two ways that you can see, Lagrangian and Eulerian Lagrangian, and also the luminosity defined by the gradient and the gradient defined by the luminosity. You have a certain gradient, you have a certain luminosity, but for the structure that is mainly this one, having certain luminosity that is given by the energy nuclear reaction, you have what you need as a gradient to propagate this luminosity. Then there is the thermal equilibrium that goes with the variation energy is equal of the energy production less than the luminosity. The thermal equilibrium means the energy doesn't change, so we need to have that the variation of luminosity inside the star has to be this part, that for the mass and volume, multiplied by the energy production, nuclear and gravitational, less the energy lost by neutrinos. As we saw, this is the energy lost by neutrinos we saw today. The neutron energy lost by neutrino during nuclear reaction is already counted in the energy production of the nuclear the reaction, because it's easier in this way. Since it is energy is lost immediately, it's just considered inside here. That actually in Lagrangian notation it's quite more simple. It's just vibration by the mass is the sum of the energy rate. These are not the only one. We have the several luminosity energy transfer. In additional, if it's just radiation using conduction, usually the conduction can be included in radiation since it's small, normally in the stars, and can be rewritten to be quite similar to the luminosity radiation. The potential for by radiation. Remembering the total luminosity, this is energy by time, by power. The relation with the flux, so the energy by time by unit of surface. For the convection is this part. Let me consider, okay, the density of the medium, velocity, how this part is moving from the convection, the difference among the adiabatic gradient and the actual gradient. As we saw, this is positive, so this means that these have to be little smaller than this one. Yeah. All the complicated part of the convection actually is added by this lambda, that is the mixing length, that is really complicated, but it's added on the problematic. Then considering the pressure, ion fraction, electronic pressure, radiation fraction, these two are considered inside for the gas pressure, radiation pressure, they are this type. For ion is just this one, the classical for ideal gas. For the radiative pressure, it's 1/3 A T to the 4. It's not, try to remember, it's not so complicated. For the electron, you have to consider if they behave like ideal gas or degenerate gas, so it can change with the obvious consequences. Then you have to consider the opacity. That is a function of density and temperature. This is the rate of energy production similar way by this coefficient. Relation among the gradient of temperature and gradient of pressure. In general, opacity, pressure, internal energy, the coefficient of transformation, that in the case of the gas, it's the adiabatic coefficient, and its production all are function of the atomic mass, the density, and the temperature. Then last, the condition for chemical composition that gives us the fraction mass, the sum of fraction mass is 1, and then the definition for the atomic mass in general and the typical value for the electron atomic mass and ion atomic mass. All this stuff combined with the boundary condition that at the center we have the mass is 0, obviously, the luminosity is 0, also because luminosity is the energy flux multiplied by the surface, and the surface and center is 0, so definitely it's 0. The density of the center is the central density, central temperature, central pressure. At the surface, the mass is the total mass, the luminosity is the total luminosity. Then there are this one, there are that density of the surface is the density at the surface, then for the temperature, superficial temperature or effective temperature, that is the temperature of the photosphere, that I remember is defined by with the opacity, with the optical depth, that in essentially it's the layer below what the matter is not so transparent to the radiation. So essentially where I cannot see more of the detail. To consider like we consider where start a fog, if you're seeing a person entering, when we stop to see well the person is where the start the fog that is surface, similar for the start. And the pressure lead. Usually, sometimes these three are just considered zero for simplicity. So that's the reason I put this one, because these are for the perfect solution, but for a simple solution, usually you put this one to zero. Anyway, this is the actual for the sun, and if you can see here, the density that is this value here at the photosphere, few kilometers below. Here are the high related to the photosphere in kilometer, up to 2000 kilometers inside the sun. The density is almost 10 to the minus 6 grams per centimeter square, centimeter cube centimeter. The air, the density of the air is 10 to the minus 3, that is almost here. So the density of the mean density of the sun a little less, around 1. So you can see that considering the density 0, it's not so not the change a lot. It's actually really low. Okay. I think this part is quite boring, sadly, but we're starting to need to put together everything we saw up to now and start to see how it's work to model a star, to create a model of the star, how the several parts varies. There are several ways a model to produce a simple stellar model. One is using a property that is considered constant, one property. You can see that it is almost uniform inside, so put that quite uniform and study the other. Obviously, temperature, pressure, density are not really good since they vary. Usually, it's considered the composition. And even if we saw that the composition changed during the time, we can have some example that a star with a uniform composition makes sense. If a star have good convection inside, it's mixed, maintain the composition uniform. Or if recently formed stars on the SAMs, zero age in the sequence, that means it's just contract start to produce start to produce because we actually the energy nuclear reaction can start definitely before. For example, lithium, beryllium, boron can have a little cycle not a natural cycle, it's just a disruption of production of helium in just like 2 million. This is the combustion of the lithium and the helium. And this is the reason why quickly a star destroy all the lithium inside this core, because it starts quite quickly, just 2 million Kelvin. But anyway, in when start the jumps, and the jumps where the energy rate for the nuclear energy rate is the mean energy production. In that position, the composition is almost the original, so quite uniform. Is still not a change in the composition due to the nuclear reaction. So it's simple model, but as a physical application. Another is using two boundary condition, the center and the surface, considering that all the properties change monolithically inside. Not always can be really true. For example, for a star where there is a lot of production of neutrinos, the energy production rate can change sign inside. We have some point that goes below zero, and some part will start absorbing energy instead of production. Or just one boundary, consider the center and calculate from the center outside. We can be sure about that we can describe well a star. That is the Bog-Russell theorem, that on the uniqueness of the solution is not actually a theorem, a real theorem, because the theorem usually is mathematically demonstrated. It is not, but it makes sense. But to say that the world structure of the star in endostatic and thermal equilibrium is uniquely determined by its mass and distribution of chemical elements throughout its interior. And considering that the question, internal energy, unit, opacity, energy production rate, and are all local function of density, temperature, and chemical composition. Considering this one, we can this theorem say that we have the mass of the stars, that is a chemical composition, and how to distribute inside. We can determine uniquely how is the structure of the stars. Is not demonstrated really well, but makes sense because there are the consideration of the number of parameters needed to solve the equation. The system we saw we have four equation main. In integration of them, we have for constant, we have parameter like luminosity, mass, radius, the other. So considering all the additional conditions, we can see that just giving mass and distribution of chemical elements, we can determine all the constant for the integration. This also means that since the luminosity and the radius depend only from mass and composition, we can change a little and have that the luminosity can be described as the temperature on the surface, effective temperature, and the composition. That is actually the Russell diagram. So, okay, it's in this way. The star, each star is put in a different point of the temperature and luminosity according to this mass and the composition. Some part of the how we can calculate after evolution tracks. Obviously, the chemical composition varies internally, is not constant. Nuclear reaction mixing process can change. If you have just a radiative transportation, you have this discussion this way. They are the original one corrected by the rate and the time, and in which if you have the convective, a little more complicated, you have to consider the part of the mass where is the convection and do a average along this part. The convection is useful for something that is really messy or calculate the structure perfect. In fact, the convection is still not perfectly determined how it's working, the mixing length, everything. So, and the evolution is just a correction of the previous state. You have this value, you just correct a little, continue. And this is shown essentially when you are looking for evolutionary tracks for stars. There are this movement of the stars along the Russell diagram. And this is how it works. And how you can understand, since the star depends on this part where is radiative and where is convection. The star usually have always this part, this both. You can see not always is perfect. In fact, exceptionally, a part of the main sequence, a part of the red giant branch, usually the top part. The other, you can see that every isochrones or evolutionary track that you consider, several versions you can see, they are not perfectly equal among them, because it's quite some part, especially with subgiant, when the star is moving from the main sequence toward the red giant branch, is still not perfectly described, so you can see the isochron can have some change in this part according to from one author to another. It's some complicated part. Numerical solution, as we saw, will not have an analytic solution for a star, but we just need to go with the numerical solution. There's several methods. One is the matching method. Essentially, you can integrate it from the center, the surface, and try to match at some point in the middle that you can choose accordingly. And this match to have a complete discussion of the star. Likewise, similar from the spline, when you have the several quadratic cube aluminium, and you match all the point to be the value the same and the derivative the same. It is
Professor.
Sim? Yeah.
Point, could you show us an example of these two numerical solutions? How to match the isochron?
I don't.
It doesn't have to be now or but at some point.
Clear example. No, also because it's essentially that you calculate the Q solution from one part to the other. Because if you start from the center, you can arrive to the surface that is deviating from the actual value. to minimize this deviation, you use 2, and then at some point you try to do small variation in the way the two values are the same. It can be the one part describing the core, other part of the surface, or up to where start with the convection, something like that. I don't know Act 1 example also because it's just a way to do the calculation. It's as a visual example, it can be like when they are building a tunnel below a mountain, something else, and instead of doing just one and going outside, and maybe you miss completely, and you are not where should be the exit, you start caving from both sides, and you meet in the center. So when you have some error, you can correct there. They are smaller. In some way, it can be half. So if you have, for example, for a street, you are putting a road with the tunnel. If you have a road from one part of and the other, if you exit to the part with an error of 2 meters, you are completely outside. It's not good. But you go in the middle, you can correct them quite easily. It's okay. This essentially is just to have an idea. It's not that nothing peculiar. How we calculate a star. We need to do calculation. You have not having an analytic solution will be fantastic because you have the formula. You just put the value inside, you get it. Suddenly, then we see that we have just a one differential equation, and we have to do calculation by number. So you have to start and see how is going. To avoid, since you are doing correction, one solution this way. Start from point from another and meet in the center. In the middle part actually, it's not exactly, it should be the mean point from the two, so half radius. You meet where it because some part can be less problem, so you can go a little deeper than the other. Other show is just going to see a theorist working on evolution track and show how they are calculating all the formula calculation. It's not something that you can see, but this is just to have an idea. The other, quite similar, is the shell method of the enery, that you divided the star in shell. You apply a solution in each cell to relax to. Oh, my internet connection is mistake. And apply the equation to each cell. You apply a small correction and to relax it to the final solution to have a perfect. This is in some points similar to the matching, only that you are dividing a star in small part. For each part you are calculating part of the solution. And mathematically, it's something really awful. I can, just by curiosity, yeah, to show, I have to study these things with actual theorists that are doing Chiosi, famous for his isochron evolutionary tracks, and this method of the shell can be quite messy. And you see that you start with the classical simple equation, and starting doing correction and everything, and start can go quickly, really messy, with a lot of equation that I decided to spare to yourself. This is because you have a system of the equation for each part, and you have to connect each shell to the other, that we have a continuity. It is the solution has to be continuous among the stars, and also the derivative have to be continuous, because otherwise something physics ask for this, that the physical function have to be continuous, and the derivative have to be continuous. So there are spike and doesn't make sense physically. Okay. This was just giving an idea. It's not simple. The calculate study the structure of the stars, but I say we start at the beginning. It's all the basics are quite complicated. You can have everything here inside, because classical physics, dynamics, but then here with the rate and the energy production rate, you have the nuclear physics. In the pressure, you have the generator. You have to study with all the mechanical, statistical mechanics, and essentially, I think all the physics, possible physics, goes inside. Tomorrow it's holiday, or if I remember,
Yeah, I think it is. Ah, yeah,
tomorrow
21 of
is
May.
the Navy, la Guerra del Pacifico.
Yes.
Also the famous talk in the Congress, if I remember. So tomorrow it's holiday. Okay. With Friday we start to see polytropes, and you see it's a lot of calculation. Sorry, this, but then after this part, we'll soon start to see actual result and something to manage of the star, some instantly result we can have like Chandrasekhar mass. It is why dwarf and has a limit in mass. It's a reason. Oh, but okay, this is just show the for the plasma neutrino process that essentially at a where is more important we saw that is the part that is really high temperature and maybe also high density. It's essentially the main processor of the pair production, the interaction with the plasma. Bremsstrahlung and photon are in a star at the beginning. It's less than can be in another situation when you have high density compact object with the temperature that is lowering other. But the mean that is here, we saw below the log here, it's 300 more or less million Kelvin. Start here, the main production is by pair or plasma, depending on the density.
It surprised me that that part, the plasma regime, I thought you had to lower temperature. It goes all the way up.
It's high density, but it's not exactly, because you need it's when the photons moving inside the plasma have the characteristic to start to behave like a boson with mass rest mass. So this means also the light are propagating with less than c. So you need an high density and usually high production of also the energy of the photon could be quite high. So it's essentially in this part that this interaction with the plasma can produce neutrinos, because this area is not where they are working. Are dominant. Here dominates the plasma. Here dominates the pair. Obviously, you are always on the production, but if you are too low, for example, you cannot produce enough neutrinos by. Now here it's the pair, so an annihilation of electron positive. You cannot enough production of this pair that can start with the photon, this part. But here it's in a way here substituting with the production of this one, so some part makes sense since a pair of electron positron have a higher mass, so you need a higher energy from the photon to produce them. Below you can produce a little more of this neutrino because there's a little less energy than the pair that produced by the photon. And at higher energy, at higher temperature, you have more energetic photons, so you can do more pair, and then produce more of the pair neutrinos. Why let's say, increasing the density, we need to have more interaction of the photon with the plasma with that process. At the end, you see that sometimes are not so, the process seems quite similar, because you can have instead of production of pair of electron and positron, you can produce a pair of neutrinos. Or then the pair of electron positron produce the pair of neutrinos. It's a little connected. Here is the photon need to interact with an ion to conserve part. Here is the interaction of the electron with the ion. So it's some similar process, but okay. In some part you can have a more where is dominant, let's say, not that it's just plasma, here just strong, just a photo, just pair. It's essentially where one starts to be higher than the other. Okay, Marcelo already done. We'll see on Friday then.
Yeah, see ya.
I don't think we have a lot of questions because this part of more theoretical checking.
Bye-bye. See you on Friday.